Okay. What's wrong with Okay. Shall we start? Yes. The sound is not good, which is perfect for this class. It's the volume, you think? Hello, hello. Can you still hear me? Well? Okay. So, much better. Last class, which was last week, oh, so much in between. We finished our design for the capacitive touch screen, where we decided that the signal that we were getting from touching and change in the capacitance was not large enough for us to really distinguish between touch and no touch in a very stable, low error manner. So we brought some new tools to our design. Okay, don't want to make anybody irritated by that. Okay, to our design, we brought new tools, and we talked about the operational amplifier. And the operational amplifier, as the name says, amplifies the signal. And we look particularly how to apply the operational amplifier as a comparator, because we wanted to compare the signal that we were getting from our capacitance touch screen when there was touch and when there was no touch. And we want to have a binary answer so that we could for sure know that that pixel was being accessed by touch or not. We also saw that the operational amplifier had different types of power sources inside, or it was built with what we called dependent power sources. And those dependent power sources could be either a current source or a voltage source. And they're dependent because they depend on our external power sources or independent power sources, such as a battery, in order to work or to operate. So we looked that inside the operational amplifier, we had these two dependent voltage sources, voltage-dependent voltage sources, and one of them was defined between VDD and VSS, where VDD and VSS are independent power sources that we add to the amplifier in order to define the rails of the amplifier, the limits of which the voltage levels we reach when we use the amplifier. Okay, so this one, the lower voltage-dependent voltage source, was basically taking the average of the rails of the amplifier, while the second voltage-dependent voltage source was taking into account the gain of the amplifier. And what's the gain of a typical amplifier? Infinite, very, very large, the gain, and multiplying that gain by a voltage that came from the two terminals here. That voltage we called the difference between these two potentials, we called VD, V differential, which was U plus minus U minus, the other two terminals of the amplifier. And then finally, in this amplifier, we would have a V out, and we use that V out as the output for our capacitive touch screen. In the end, what we got to was a model where we had our capacitors, we had our third screen here, our third switch here that we were using in the different phases. And we connected the U plus terminal of a comparator to the capacitive touch screen, and we connected the U minus terminal of the comparator to a voltage that we called voltage threshold, which would be a voltage that would define when we had touch, when we had no touch, and take into account the errors that we had in the measurement. Okay, that's what we did last class. We also, it was a loaded class. I also gave you homework. I said today we are going to do a new design, and we are going to play music and have a party. And I gave you specs for the design. I explained what the problem was. I said you guys have tools that I gave you so far. And then I asked, okay, how can we go from playing music that is a digital signal to playing music very loudly using an analog device such as a speaker, when the speaker has a spec of 0 to 10 volts. That's the operating voltage that you give for the speaker. And what else did I say? That's it. So the problem was, how do we go from digital to analog, and how do we play music very loudly? Using the tools that I gave you. Did anybody try to sort this out? A little bit.
Doesn't look like.
Doesn't look like.
No. I mean, is amplification important? Is amplification important?
Luckily, we're not in Zoom anymore. When you had your headphones, yeah. Okay, so any ideas? How do we do this? So, if you were the designer and I was your boss, what would you tell me? Sorry. Oh.
Fired.
Oh. Sorry. It's a good start. Sorry. The tools you gave me cannot do this job. It's true. There is a new element that we are going to start today that actually can do this job. And guess what? It's called digital to analog converter, which is exactly what we want to do here. Now, I told you, keep coming to class because every class is really fast now in terms of new information. So what's the digital analog converter? Digital to analog converter, its nickname is DAC. And it's a device that looks like this, where you have resistors that are going to take the bits, the digital input that you have, and that can be 8-bit, for example, this example here, an 8-bit DAC. So you take 8 inputs, 8-bit DAC, and then the input goes through a resistor. Okay, resistors, you know, they use energy, they use power, but you know how to analyze resistors using Ohm's law. Then we have an amplifier here, okay? And that amplifier is taking the input from this series of resistors. There is this other resistor here, and then you're going to measure the output here. And this output will be an analog output. See that in this case, the U minus is connected to the resistors that we have in this device, and the U plus is connected to ground, 0 volts. All right, is this a difficult circuit to analyze? Not really. You know already the amplifier, you know the resistors. So by the end of next class, you will be super comfortable analyzing this circuit, okay? And we are going to use some of the tools that we have in order to analyze this circuit, which is, when we have something complicated, equivalence, right? Okay, so let's do the design then. Now that I gave you the digital to analog converter, all it does, takes digital signal, runs through a series of resistor and an amplifier, and the output is an analog signal, which is what we want. So when we go to our design, this is how it looks like. In our design, we have our iPod, because Mickey and I loved the iPod. It was the first time that you could get digital music. No? It was the first time I could, yeah. You could before, yeah.
I mean, CD.
CD, yeah.
CDs was digital music. Or,
portable though.
Or computers.
Oh, portable, yeah. But the iPod was amazing. So here, I am storing my, my late iPod, digital data, digital music. And now I want to take that digital data, play it through speakers, and have a party. Oh, still, yeah.
It might be me.
It was you? It's strange because typically it works. I don't want my volume too low. Okay.
When we talk about positive feedback, then.
That's going to be a problem, yeah. Oh, today I also have that. Okay, so how do we do this? I showed you, for us here, we have our specs. We want to go from digital to analog. We know that the speaker is going to take 0 to 10 volts. Here we are going to get 0 to 10 volts input. And that's all I gave. I can give you another spec. The DEC usually goes from 0. See, I'm putting the limits here, the VSVDD, or the limits of the DEC, to 0 to 3.3 volts. That's VDD. 0 is the ground. And now we need to model. How are we going to model this in order to come to a language that we all understand? So that's when we use equivalence, right? So if I show you this circuit here, and I ask you, well, how would you model this circuit in a way that we can deal with using equivalence? What would be the components that you would put on your equivalent circuit? Remember, the equivalent circuit is either I Norton, where you have a current source and a resistor, or V Thevenin, where you have a voltage source and a resistor. So what would you pick as an equivalent circuit for this? Wakey, wakey. Thevenin or Norton? Thevenin. I like Thevenin too. It has voltage source. I gave you voltage values. It has resistors. We saw that the DEC has many resistors. So I'm going to say that the equivalent circuit for the DEC is going to be a voltage source that is a signal, right? Remember, we started using voltage sources squiggly, but we still call this voltage source V Thevenin. And then we have a resistor attached to it, and that resistor is going to be R Thevenin, the equivalent resistance. I'm going to ground this part of the circuit, and here we go. This is equivalent circuit for the DEC. So I'm going to put this nice DEC here in a square and say, okay, this is the equivalent circuits that we are going to use for the DEC. Happy? Okay, we know that we're going to ground this other side of the equivalent circuit, and we can measure V out from here when this is also connected to ground, right? We know that part, which will be the V out of the DEC of the digital to analog circuit. Okay, now how could we design or represent the speaker. Which element do you think is the best that we have in our pockets to represent a speaker?
Which one?
You have to speak loudly. I don't hear very well. You said? Okay.
Resistor?
Resistor. Yeah, very simple. Very simple element. An element that is consuming power. Seems good enough to me. So I'm going to put the speaker here in green. And we could represent the speaker as a resistor.
It's 16A, but 16B,
Yeah.
you learn something also in addition to that.
In addition to that, yeah, I know. We should teach 16B
Oh yeah,
one day.
one day.
Next semester. Oh, that's nice. Okay. All right. So then we have all the elements, right? We have here all the elements we need. We have here our representation for the deck. It's taking the information here, our signal that is digital. And then if we connect this part of the circuit here, our V-Thevenin circuit to our speaker, we should be able to get an output that gives us the response or a result at least. So let me just copy the model that we have here for the deck, right? Which is a Thevenin model. With Thevenin, or Thevenin. And I'm going to say, and it's from your notes, that the resistance for a deck, the equivalent resistance for the deck is about 1 kilo ohm. Okay? Then we have that model, and for our speaker, we have the model of just having one resistor, which is the resistor representing the speaker, and that resistor, speaker, is typically of 8 ohms. Okay, and that's why equivalence makes sense, right? Because when I gave you that circuit there, oh, there's all these resistors, but you know how to deal with those resistors. You know how to find one resistor value that is equivalent to all of these resistors, right? That's what you have been working on homework. Okay, so now we take our parts here of our model, we connect them to form our circuit, and then we see what happened. Do you have a question?
Yeah.
Go ahead.
So why didn't we use an op-amp to model a speaker?
Why didn't we use an op-amp to model the speaker? Okay. What would be a good reason to use an op-amp?
Don't we need to make a decision about the sound, like, level or volume?
The volume. We want to make a decision about our output, which coming out of the deck needs to give us something between 0 and 10 volts. But as long as the output of the deck gives you that voltage, the speaker should work.
Okay, so there's no decision that needs to be made, it's just...
No, as long as you are within that range, then you're working. So we have to make a decision on how to model the deck, because this output here is what you're going to feed into the speaker. So this output needs to give you between 0 and 10 volts. Okay, then if I put an op-amp here, my circuit gets a bit more complicated, and the speaker, simple way for now.
I mean, one way you think about a speaker converts some form of electrical energy to audio energy, so it dissipates energy.
Mm-hmm.
What other device do we know about that dissipates energy?
Mm-hmm. That's right. Okay. And it's dissipating energy because it's mechanical. Right? It's mechanical. All right. So once we have this circuit here, I can ask you, what is the voltage that you are getting here at the speaker, which I'll call V speaker? Why do we want to know? Because of your question. We want to make sure that V speaker is between 0 and 10 volts. So now I ask you, what's V speaker? Okay, you know what V speaker is because this circuit is a well-known circuit to us, right? It's a block for us, which is the voltage divider. Yes. So because, again, we are doing equivalence here, and we have blocks divider. We have blocks. We know answers already. So we can say that V speaker is going to be equal R speaker over R Thevenin plus R speaker times V Thevenin. Okay. So we know that our speaker is 8 ohms. We know that our Thevenin is 1 kilo ohm. R speaker is 8. So what's that ratio over there? V speaker equals V Thevenin over 126, I believe. Did we achieve what we wanted? Are we going to have a loud party? No, because V speaker is so much lower than it should be.
It should, yeah.
Right. It's not the type of
What? I can hear you. I can hear you.
What?
What?
Okay. No. We wanted to amplify, right? We want to get voltage that was between 0 and 10, and now we are dividing the voltage because the arrangement here was not the perfect arrangement. And this has a name. What's happening here? Do you want to say, Mickey?
I'm just overloaded
You're
by...
just overloaded the
Overloaded.
information. Okay. So it means that when we connected the deck to the speaker, there was some sort of loading effect.
Oh, loading.
Oh, yeah, loading effect.
Oh.
Yeah. And because of that loading effect, that means that the way we connected things was not right. We did not achieve what we want. So our next step will be to isolate those two components so that we get rid of that loading effect. There is a question.
Can't we just make V Thevenin something really big so it gets to 10 volts? Well, I guess.
Yeah. Would that be an efficient design, though?
Perhaps. Probably not.
So if you want to get 10 volts, what would V Thevenin have to be?
1,260 volts.
Yeah.
Wow.
Perhaps we don't want that.
I don't want that in an iPod.
Mm-hmm.
Our speaker instead.
I'm sorry?
Could we increase our speaker instead?
Our speaker, because equivalence works, and this type of model, simplifying reality works, as long as you are in touch with reality, right? And since we are talking about a speaker, yeah, you know what's you know what the ballpark. I could have done maybe 10 ohms just to be ballpark, easy to divide or deal with 1 kilo ohm, but yeah. Okay, So what we have to do is actually to isolate our digital to analog converter, the DAC, from the speaker. And we have to isolate it because we still want to amplify, right? We want to get a voltage that can then talk to our, well, give the output that we want for the speaker. So now that we have experienced with this design, now we can put what in the middle, between our DAC and our speaker? What would make sure that we are giving the right output? What tool do you have in your pocket that allows you to select limits, voltage limits? Op-amp. Op-amps. They even have nicknames in your life? That's lovely. Op-amps. Okay, the op-amps, right? Because now it's what you were asking. I don't know your name, sorry. Okay, Ian. What she was asking, why don't we use an op-amp? Now we can use the op-amp because in the op-amp we select VDD and VSS. And we can select VDD and VSS to be limits, the voltages that we want in our design. We already saw that in the capacitive touch that VDD and VSS could actually show us touch, no touch. So we can do the same here, right? So I will draw everything. Let me copy our design here. Carry it over. Now we are going to break this down by taking this part away. Let's see if it works. Yes. So we want to isolate these two. And in the middle here, we're going to put an op-amp. Okay. I'm going to start labeling things here, okay? To make this connection very nice and clear to everyone. You can go away. Okay. Now, the op-amp. First, I'm going to make a big op-amp here to remind you of the symbol. So the op-amp, oh, too large. Because it's still a relatively new thing for us. So the op-amp will be something like this. That's going to be isolating the DAC and the speaker. Okay. What are we going to have in our op-amp? We are going to have two terminals here that we can use to connect to the universe. One that is U+, one that we call U-. Then we are going to decide what we are going to connect where, okay? Then we are going inside the op-amp. We know that there are two voltage dependent voltage sources, where this one is VDD minus VSS over 2, and this is connected to, what do we connect these to? VSS, very good. Then we have our second voltage controlled voltage source here that is connected to VDD, and this one is given by A, gain, op-amp gain, times VD. Do you remember what VD was? The voltage differential is U+ minus U-. Very good. Okay, and we know that this VD is here, right? VD, voltage differential. It's the voltage across the two terminals of the op-amp. Okay, now, friends, decisions. Decisions. What would you pick VSS and VDD to be? Some value, but I gave you some idea of which value. 0 and 10 volts, that's an option. What other options would be? 0 and 3.3. But then you just have you're only using what the DAC would give you, right? Since we have an op-amp there and we know that we can go from 0 to 10. Other ideas, numerous combinations of numbers that can give you 0 to 10 volts. Minus 5 to 5, that would?
The direction doesn't matter. Then the direction of U plus and U minus.
Oh, interesting, yeah. I like, the suggestion here was minus 5 and 5. Because then you could say, okay, if I say VDD is equal to minus VSS, which is equal to 5 volts. That's what she said, right? That was his suggestion. I like that suggestion. Why? Look at our diagram. Over here, we have a voltage controlled, dependent voltage source, voltage controlled voltage source that depends on VDD and VSS. So when we have VDD minus VSS here equal how much? When we do VDD minus VSS, what do we get? 0, right? We cancel them. And that would be nice, for example, to pick limits where you could cancel things out and make your life easier. Okay, so these would still give us a 10-volt output. Okay, and other question. Doing our voltage definitions. Our voltage differential in this case would be U plus minus U minus. But U plus and U minus are leads coming out of the op-amp that we can use to connect to other parts of the circuit. So where do you think we should connect the circuit, the equivalent circuit for the DAC? U plus or U minus? U plus. Okay, so let's, I'm going to take a wire here. Oh, let me make a red wire. And connect here, okay? So now we connected the DAC to our design to U. You have a question? Okay. Let me just finish the arrangements and then we can ask a question. Oh, that's where you are. I was missing you here. Okay. We connected the DAC to U plus. Now, what should we connect to U minus? We could connect ground. That would mean that we would be connecting this voltage here to 0. But since we are comparing things and we want to have some sort of reference, right? It would be also useful to connect here our U minus to a voltage source that is a reference voltage source. A voltage source that we know. And then we connect that to 0, and I'm going to call this Vref, reference. Now, with this arrangement, that means that our voltage differential would be given by the V Thevenin, the equivalent voltage for the DAC, minus this V reference, which would be something that we know when we chose. So you always want to choose things to simplify your life. Okay, I know, it's coming. And then, where would we connect the speaker? Where would we connect the speaker? V out, very good. So V out, I'm going to make a wire here and say, okay, this is V out. You could also say, okay, V out is here, okay, from that note. I'll say, okay, V out is connected to V speaker. Question.
So I was just confused earlier about why VDD minus VSS is 0 and not 10.
10? Oh, did I get my polarities wrong? Yes. VDD is equal to minus VSS. So it will be minus 5 minus 5. That's 0, right?
It's like 5 minus negative 5.
Oh, yeah. It's my polarity is wrong. Okay, thank you. But I'll show you that it will cancel out anyway. We'll leave it like that because we are going to play with it later in the other questions. There's one here, there's one over there. Run, Mickey, run. Okay, what's your question meanwhile?
Why is there a VDD on the top? What does it do?
The VDD is always at the top, right? Remember the op-amp had two rails, VSS and VDD. Those are the rails of the op-amp. Yeah, let's see if I have a slide here on the op-amp. Op-amp, yeah, remember VSS, VDD. Yeah, and we did the analysis of the op-amp last class. Yes, go ahead.
I was a little confused. I understand why U minus is equal to V ref, but how is U plus equal to VTH? Because isn't there a voltage drop across the RTH?
Excellent question, excellent question. What's the model that we had for the op-amp? And when I designed this, okay, when I started this, I had the op-amp like this, right? Let me erase that, like this. So what are those connectors there? What are those leads from the op-amp? U plus and U minus. What are they? Which elements are they? How could you model that element?
Open circuit.
An open circuit, thank you. And then, what's the current flowing through an open circuit?
0. So
Zero.
there's no voltage drop.
So if the current is 0, well, then I know if the current is 0 in this node, then I know that the voltage here is the same voltage from that node. Excellent question. Thank you so much for that. So it's the model of the op-amp. We have those two leads. Those two leads are modeled as an open circuit, and open circuit we know current is 0. That's always the case, by the way. And we will see that this has even a special name for op-amps. Okay, now, question. What's V speaker in this case? Which was our quest here. We wanted to find out what V speaker was. So what's V speaker? How do we find out V speaker? Which tool do we use? Well, to find out V speaker, we want to be looking at this circuit. We know that V speaker is right here. So if we look at the loop that V speaker is connected to, what can we do here? We can do KVL, right? So if I go here from ground to ground, I could find V speaker. So I'm going to write V speaker here is going to be equal. It's going to be equal VSS, coming from the bottom here, VSS, plus this voltage controlled voltage source, VDD minus VSS over 2, plus A times VD, which is U plus minus U minus. Then do we need to consider VDD? Not really, because different node, right? Okay, so I'll just write down what I just said, and if you were following here with the laser, I'll do it again. So it will be VSS plus VDD minus VSS over 2 plus A times VD. Okay, I need more space. Sometimes it gets too crowded. There we go. Okay, so what did I do? I applied KVL here for this loop where V speaker is, going from this voltage minus to plus, minus to plus, minus to plus to here, minus to plus. So I have VSS plus VDD minus VSS over 2 plus A times VD equal V speaker. Okay, thank you for answering her question. Her question was, what did you do there? How did you get that to be? Which loop is this? I'm confused. So pay attention here to my laser. Okay, we are interested in finding out what's V speaker. So here we go, minus to plus, right? V speaker. That's our goal. Now, V speaker is part of this loop in the circuit, right? Both leads here are connected to ground. So I apply KVLs to this loop. So to go to minus to plus, which is V speaker, I need to go minus VSS to plus, right? So VSS plus that equals V speaker. Okay, now we can simplify a little bit, and we say that V speaker is going to be equal VDD plus VSS over 2. What did I do? Here I had a whole VSS. Here I had half of VSS. Okay? So I'm just writing, flipping. It was 2 VSS over 2 minus 1 VSS over 2. That's 1 plus VSS over 2. Okay? So here on the term and same term plus AVD. Okay. Now we know that this is true, this analysis is true when we have our gain multiplied by U plus minus U minus in between the rails. This was our definition and our design of the op-amp, because we know we put the rails there, we put those two known voltages there to know that our output is going to be in between there, okay? So this is true when we have those conditions, which we do. Okay, now let's see. Let's see what happens. So that means that now, because we had, here's where the cancellation comes from. Because we had VDD being minus VSS, now this term here goes to 0. Yeah? And when this term goes to 0, we are left with only this. Clear now? Now let's do implication of this design. So in our design, we had a V reference that's for the digital to analog converter. So I'm going to put here, this is 0 volts. Let me make it a different color. This is 0 volts. And then on the top here of the digital to analog converter, we have 3.3 volts, right? And this is our V-Thevenin. That's how we are. Then over time, we are going to look at the signal over time. We also had a reference voltage that I'm going to put here and call this Vref. And Vref was a voltage that was fixed, right? We put an independent voltage source there. It's a voltage that's fixed. And what do we know? We set our circuit such that when the signal is higher than Vref, it goes to VDD. And when the signal is lower than Vref, it goes to VSS. That's the reason to put that Vref there. So let's play nice. Ready? Mickey, do you want to play? Play nice. Maybe classical music here. Oh, you're going to sing for us. Oh, this is going to be very nice. want is to see what's happening in the speaker. And that's where we are looking at the output. So let me label the output. Our output is going to be like this. So if I have the out here, we set our limit to be plus 5 volts minus 5 volts. What does that mean? That means that when our signal here is lower than Vref, the op-amp rails and our signal goes to...
Can I do that? Can I do that too?
Huh?
Can I do that too?
In a moment. You want to do it before?
Together.
Oh, yeah. So, yeah. It went to VSS. Now, when our signal is above the reference, what happens to the nice music that we were playing? It goes to VDD. And then it will go down again to VSS. And stay at VSS until it goes up. Yeah. What did we create here? A
Distortion.
nightmare.
Distortion. What did we create here?
This was a nice sound. We took a nice sound. We created something else. I don't have words. How should I describe this? Noise. Oh, it's
Distortion.
a nice sound. And we got noise. Terrible noise. But it's not in the sense of signal noise. Okay, so it means that our design is getting a little bit better, but it's still away from the nice party that we want to have. Yes, go ahead.
So I had a couple of questions. One was, is distortion when you like clip the signal once it hits a certain point, or is it like once it passes a threshold, it goes like from -5 to 5?
Yeah, so in this case, it's really, we were passing the threshold, and in our design, we were just throwing the signal to VDD and VSS. VDD and VSS based on that reference that we had. So that's why the sound was completely distorted. It was not what, okay, the signal was completely distorted. It was not what we started with, right? That means that our amplification was too much. Okay, so what we need is, again, new concept, new tool for our design to take into account this problem, because everything that we picked was reasonable. We picked the right ranges for the voltage, that those ranges were chosen to have the speaker working well. We picked a reference, and we could distinguish between signals above and below the reference, but we didn't have something to correct for that distortion. And it turns out that we are going to apply now something that we use a lot in our lives, which is negative feedback. Yes. No, you don't want?
Well, I don't think you're doing well.
Really? But I try so hard.
I'm just giving you negative feedback.
Okay. Then I'll change things, Mickey. What do you think I should change?
You should do better.
That's one type of feedback. Yes. Let's see. In real life, where is negative real systems? Doesn't need to be emotional, like Mickey just threw me off of the bus. In systems, where do we see negative feedback? Our body is amazing to do negative feedback, yes?
I was going to say grades.
Grades?
Yeah.
Oh, really?
Yes.
What happened? What's the negative feedback? You see your grades and you say, oh, I am doing well. That means I should exercise more. Yeah? Okay,
I
what's
have
your
a good one
example?
for about grades, if we don't want to talk about it.
Huh?
About grades, it's good. Let's say midterm 1, the grade was super high, so the faculty go like, oh, that's too high, we're going to crush them on midterm 2.
Yeah.
That's negative feedback.
That's feedback on the grades. Yeah. There are more examples. Yes. Hold on.
Balancing?
Balancing. That's right. When you try to balance, your body is doing all sorts of corrections so that you can do a triples. Yeah? Very good. Others. What about food related? Does the body give you feedback depending on what you eat? What happens to the body if you eat a lot of sugar? Insulin production, right? Releases insulin to help you. If you keep eating sugar, yeah.
I was going to say like a thermostat.
Hmm?
A thermostat.
Uh-huh.
It'll keep a certain temperature. If it gets above, it'll cool down, and if it gets below.
Exactly, because it doesn't want to overshoot the temperature. Yes? Cars, do we have drivers here? Many modern cars have sensors, right? If you are not driving straight, you will feel a little pull on your in the steering wheel, telling you, oh, that's negative feedback right there, correcting. So negative feedback, it's a signal, or it's something, an event that allows you to correct. Okay, many examples. You can keep thinking now, you'll find much more examples. In design, when we are designing a system, very often we use block diagrams, like the one I have here. And we are going to start using those block diagrams more and more, because it gives you an idea of your entire system, and it's a good way to give yourself feedback on how well your design is doing. So typically, so far in this class, we only looked at the top here, right, of our system. We had some sort of input, which would be a sensor or a voltage, and that input would go through a block. Here's a block. This block has also a function. Because it has the plus here, it means that this block is adding. So it could be an amplifier that's adding things. We had blocks that we used that were comparing, right? We had blocks that are amplifying. So the signal goes through that block, and some sort of addition happens. And then, because we are coming with a signal, signals are never perfect, measurements are never perfect, we always have an error associated. So the output of that block in this system, I'm saying, is that it's whatever signal you got plus some sort of error. Then that signal and that error goes into the amplifier. And once it gets through the amplifier, you have an output that took into consideration your signal plus your error, amplified it, and put you as an output. That's when we get this distortion or this terrible output of our data, because we amplified also an error. So what you do to correct for that, you take parts of that information, that signal, that output, parts of it, and you feed into a block that is going to be your feedback. Okay? So once you have this block, which is your feedback, and you are processing part of the data, now you take it here and you feed again through that first block from the negative sign, which means that now you are subtracting the information that you had that you're using as feedback, parts of the information. For example, the initial feedback that Miki gave, I'm just going to use doing well and forget about the other part of the information. That will be my feedback. So you take parts of it, feed into your input. Now, what comes out of this block is no longer just the signal plus the error. It's actually the signal plus the error minus the feedback that you gave to that initial block. And that's what allows us to do little corrections. Okay, if we had to start transforming this block diagram to our language here, this input, we could say that is the signal into the system, right? Then what comes out of this first block here, our addition, we could call the signal error. What's coming out here from the output, we say, okay, it's the signal output. Eventually, we are going to transform all these to voltages and currents because that's what we do here in circuits, right? Then you would have a signal feedback coming out of the block feedback going into the loop. So let's write equations for this. What is signal error to start with? Just look at the block diagram. You have signals coming into a block, coming out. So I'm taking here, now taking the full diagram. What's our signal error? It's signal in minus signal feedback. Yes, I hear murmurs still. Speakers using the first equivalent circuit. Okay, everybody following where I got this? Signal in minus signal feedback. Okay. Then I just looked at here what's coming into this block. Well, what's coming out of this block? The signal in and minus the signal feedback, because we are feeding in the minus terminal. Okay, what's signal out according to this feedback, according to this block diagram? S error amplified, yes. I'm going to write as A, which is the amplification factor, times S error. Yes, precisely. Okay, and what's the signal feedback? What's signal feedback? It's just blocks with letters with functions. Look, stare at signal feedback. What is it? It's whatever signal is coming in, which is S out, plus the function of that block, which is a multiplier by F. So I'm going to write F times S out. Okay. Now, what we want to see here is we always want to look at the signal out, right? And we are using some amplification. So I'm going to rearrange these equations to give us a relation between what's the signal that's coming into my system and the signal that's coming out of the system. Because that's what I care, right? We had the nice music. We want a signal out that's still nice music but loud, right? That's the problem that we have. So what we want to achieve is a relation between signal out over signal in, okay? So I arrange these equations to give me that in terms of things that I can control. Because if I know what is the dependencies that I have in my design that are affecting my signal out, knowing how my signal in is, then I can make decisions in my design to control the output, which is what we want. Okay, so I'm going to write signal out over A equals signal error. Okay, so I'm going to color things here so you follow. I'm writing here. Hold on. Now I need the bigger one. Okay. I'm writing here signal out from this equation over A, and that is equal to signal error. But I also know that signal error is signal in minus signal feedback. So I'm going to write this, to combine these two equations, do some substitution to give me an equation that has signal in and signal out in the same equation. Okay. Now, I can take the definition of signal feedback, different color. Look here, signal feedback is F, this multiplier, over signal out, times signal out. So that's also a good equation to substitute here, because now I can say that signal out, just rewriting, is going to be 1 over A, sorry, no equal. Signal out times 1 over A, which is what we had there, plus F coming from the signal feedback substitution is equal signal in. Okay, so started off with this purple equation here, signal out, isolated signal out over A, took the values that we found for signal error, substituted here, and now took the values that we found for signal feedback, substituted here. Now we have an equation that relates signal out and signal in by saying, okay, signal out over signal in equals 1 over 1A plus F. Okay, this can also be written as A, which is the amplification block, 1 plus AF. Okay, Mickey, this is the time that you do your thing.
Look at the aha moment.
Hmm? Yes.
Wow.
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 Is this an
Is it-
important result?
It's like a transfer function.
Is it?
Wow. This is like,
Wow.
oh my God. I mean, wow. Wow. I have no
This-
words.
This is called transfer function. I will put some words to the wow.
Wow.
Look at our design. Now we say signal out over signal in depends on factor A, which is an amplification, factor F, which is a division, our feedback, which means that we can control the output of our system by picking A and F correctly. And we are going to do this today. Oh yes, we will. Okay, so that's, let's see. There are more things that we can do for the transfer function. To finish this up, let's consider these results that we had here. Signal out over signal in, that is equal amplification over 1 plus amplification times F, right? Which I just copied from the other slide. Let's say we use an amplifier. If we use an amplifier, what's A?
Wow. So large.
So large, it's infinite. So if I make A very, very large, which we know is the output that you get from an amplifier, what happens to this transfer function?
Whoa.
S out over S in is going to be equal 1 over
What?
yes.
Even though you amplified by like infinitely, it's still like 1 over F.
You still get 1 over F. Exactly. So when we use this infinite amplification, we can pick the right feedback to get the right output. Isn't that beautiful? Oh my gosh. In my notes, I have much.
Well, even if you have like a lot of
Oh.
variation in A, like it's almost infinite, but it's like it's
all the arrows,
wow.
all the stuff, you pick you pick the right feedback function, and you have a beautiful result here in your hands. Oh, star, star. Very good. Let's go back to our...
So useful.
I know, I know. Let's go back to our design. We started off here, and we said, wait, let's isolate the DAC from the speaker, because that was not working. It was bringing the voltage down. We put together with an amplifier, then we distorted the signal. Now, let's apply negative feedback. How do we apply negative feedback now? For the negative feedback, we want to take a portion of the output and feed back into our system to correct the result. So, here we have our system, where I have V Thevenin, and I'm going to connect V Thevenin to U+, to try to do this portion. Now, that's our signal, okay? And then I'm going to take this negative part here, this negative terminal, and I'm going to connect this to my feedback block. Now, I ask you, my friends, what is the block that you have in your hands that can take part of a signal?
No.
What is the block that you can take a voltage and then
What?
the output of that block will be
Like
part
divided?
of the voltage?
Divided?
Kind of divided, yeah.
What?
I know.
What?
Yes.
No.
So look at what we can do here. We can now take a nice voltage divider that we have been playing with so much. Put right there, R1, R2, and now let's close our loop, okay? That's right. And then when we take here, the voltage right here between these two resistors, we know that that voltage is going to be divided, and it's going to be part of the voltage that was coming out of our system, which was the output. So let's connect the block diagram to our circuit. Pay attention here. I'll give you time to write down later, okay? In this case, okay, in our block diagram, what is U+? Which signal is U+? Signal in, thank you. Yes. What signal is V out? Which is our V out here? Here's which signal is V out? S out. Okay. Which signal we have in our diagram here that is U minus? Signal feedback. Yes. And finally, what is U plus minus U minus? But according to our feedback block diagram here is S arrow. Yes, isn't that nice? We have been calling this differential voltage is the S arrow, right? It's taking U plus input minus U minus. Very good. And now we know that we have everything that we need in order to solve this, this circuit, because now we have negative feedback. What are we going to do here? We are going to take part of V out, which will be voltage divider. Then I take half or whatever fraction I decide, and take here and feed back on the minus, U minus, and we know that the voltage here will be U plus minus U minus. So now I'm taking into account S in, and I'm taking into account minus S feedback, which is what we got here. Shall we do the analysis for this? We have plenty of time. So let's do the model. I know. It's so nice. Everything comes together. Model. Okay. Here is just nicely drawn like you have in your note, where we have V Thevenin, signal coming in. Here's our amplifier. Here's our voltage divider connected to U minus, giving us voltage feedback. Okay, let me do some labeling here for consistency. So here I have U plus, here I have U minus. R1, R2, VSS, VDD are there. Okay, so let's do it. Questions. Let me ask questions to guide you to the solution. Okay, so when I have a op amp like this, where you have U plus and U minus, V out, what's the model that we had? We had the model that the op amp is an open circuit, those leads, right? So what would be the equivalent here? The equivalent design would be something like this, where I have U plus, I have U minus, and I know that the voltage between those terminals is equal U plus minus U minus, and that's equal to our VD for now. Okay, now we know that in our models there is a current. We could say there is a current going here, which we would call I in. And what is that current? What's the current going into the op amp?
What's the current?
0. 0. You can say 0 because it's an open circuit. Okay, now we also know the other model. Inside the op amp, what do we have? We have a voltage controlled voltage source that is given by A VD. And then here we are going to have V out, right? That's what inside, let me color here. That's what is inside this guy here, the op amp, is that. Why can I neglect the other voltage? The other voltage controlled voltage source that I had there? Because we can pick VDD and VSS to cancel themselves, right? Then it becomes a simpler model. Okay, let's do the analysis. Number one analysis we already have done, which is VD, the voltage differential, is U plus minus U minus, which is going to be, what's U plus? V in. Minus, what's U minus? V feedback. Okay, second thing that we know about this circuit. What is V out? A times VD, that's right. Thank you. Now, third thing that we know about this circuit. What is voltage feedback? It's our voltage divider, right? This you should say like a chorus, a happy chorus. Oh yes, I know what's going on in the circuit. Yes. Yes, which is R2 over R1 plus R2 times V out. Very nice. And you know what this term here is? Maybe this is too dark for highlighter. Okay, do you know what this term here is? Yes, thank you. This is F. Now, can we pick F? Yes. We can pick resistors. So in our model, if I want the amplification to be a factor of 3, because the DEC, right? We want an amplification of 3. How would we select these resistors here? What's the ratio that you want for an amplification of 3? With resistor ratios, come on. 1 to 2, yeah, would give you an amplification of 3. Very good. Let me conclude here the analysis so that you get, you see the equations that show you that. Let's say I have V out. Let's say I have V out. Now I'm going to write V out in terms of amplification. So, as usual, I'll color here, V out. It's amplification times VD. So, V out is going to be A times VD, V differential, which is V in minus V feedback. Okay, so V out is equal amplification times V in minus, what's V feedback? V feedback is our function here, right? So let's see, how did I do on my minus F V out. Okay, so now I can write this as V out, like we did just for the block diagram, times 1 plus AF is equal A times V in, which is the same result that we got for the block diagram. Now pay attention, because now there is a new gain here that we are going to define, which is from these equations. So I'm going to say that the gain of this system is defined by V out over V in, which is the relationship between what's the signal that you are getting out with respect to the signal that you got in. And we know that V out over V in, based here on our little math, is going to be A over 1 plus AF. For the amplifier, we know that A is infinite. So when I take A to infinite here, this leaves me with this gain, AV, that I just defined here as V out over V in, being equal 1 over F. Thank you. And in our case, our F is the voltage divider term. And now you can see that if you do 1 over F, when F is defined as R2 over R2 plus R1, is going to give you 1 plus R1 over R2. So when you pick the right combination of resistors, you want to have a ratio here that this number will be 2 in order for you to get a gain of 3, an amplification of 3 in your system. Okay, so